This is a short video on how to write formulas for some sequences. We've looked at a good bit of problems with figuring out convergence or divergence of sequences in class. There are several ways to look at a list of numbers and come up with a formula for that. So a very, very simple example would be if I have the sequence 1, 2, 3, 4, 5, and then so on. One way to write a formula for that would be a sub n equals n for n greater than or equal to 1. Obviously, then if n is 1, the sequence value is 1. If n is 2, the sequence value is 2, and so on. It's important that you could also look at that and say, okay, it's an equals n plus 1 for n greater than or equal to 0. Those are probably the two most common ways to represent this sequence. You could even do it this way if we wanted to. So if we wanted to say an equals n minus 7 for n greater than or equal to 8, where the sequence just starts at the 8th value, we're also able to do that. In each of those three representations, it's important that you can also write it this way. So we can write braces around the n and write n equals 1 to infinity. We could write braces around the n plus 1 and say, okay, it's the sequence from n equals 0 to infinity. And we could put braces around n minus 7 and say it's the sequence from n equals 8 to infinity. The way we defined sequences is the domain is all integers greater than or equal to some integer. So in the first representation, it's all integers greater than or equal to 1. The second one, all integers greater than or equal to 0. And the third one, all integers greater than or equal to 8. Okay, so let's look at some more difficult examples and try to come up with formulas representing those. So there are two broad categories of sequences that are the most common or the most simple, I guess, to write formulas for. So the first one is an arithmetic sequence. An arithmetic sequence is one where in order to get from one term to the next, you add the same thing every time. So an example of an arithmetic sequence would be 2, 5, 8, 11, 14, 17, 20, and so on. So in this sequence, we're adding 3 every time. So one way to express this sequence is to think that this first term, the 2, is actually the 0 term. So that's A0. This is then A1. This is A2. This is A3. This is A4, and so on. If we do that, then we can think that to get to any term, we have added 3 a certain number of times. So for example, to get to the A1 term, to go from 2 to that term, we've added 3 once. To get to the A2 term, to go from the initial term 2 to the term 8, we've added 3 twice. To get to the 4th term, to go from 2 to 14, we've added 3 4 times. So if we think of it that way, then an is 2 plus 3 times n, because when we multiply by that n, that indicates the number of times we should add 3. So for instance, a sub 4 is 2 plus 3 times 4. That's 2 plus 12, which is 14. So the formula works, which is good. But the more important thing is we're thinking, okay, this 4 indicates the number of times that we should add 3. For A0, we shouldn't add 3 at all. And so it's 2 plus 3 times 0, which is 2. For A sub 1, we should add 3 once. So 2 plus 3 times 1 is 5. And none of this stuff that I'm writing over here is necessary to do the problem, but it's the way we think of it and the way we know that what we're doing is working. So let's get rid of this and try another example. So in that previous example, we're talking about an equals 2 plus 3n, obviously for n greater than or equal to 0. We could modify this to start somewhere else, but let's go with this for this first problem. So okay, let's look at another one. So if I have, say, 7 and then 3 and then -1 and -5 and -9 and so on. So here we're subtracting 4 every time, or we're adding -4. So because we're adding -4 every time we're considering this, or this is considered an arithmetic sequence. So here again, if we talk about this first term 7 as actually A0, and this is A1 and this is A2, we can think, okay, to get to the second term, we should add -4 twice. So if we do that, we're starting at 7, and then we're going to subtract 4 or add -4 a certain number of times. And so we're going to multiply by n, where if n is 2, we should have added the -4 twice. If n is 3 for A3, we should add the -4 3 times. And so we can check that this works by doing, okay, A3 is 7 minus 4 times 3. That's 7 minus 12, which is -5. So that does work. Again, we don't need that part to do the problem. This is the sequence for n greater than or equal to 0. We could use braces and write 7 minus 4n from n equals 0 to infinity and mean exactly the same thing. I think this is usually easier for people to look at, but it's the same idea. Let's also look at if we numbered these a little bit differently. So if we actually did call this 7A1 and this 3A2 and this -1A3 and so on. So we're going to think of it the same way. We're going to start with 7 and we're going to want to add -4 or subtract 4 a certain number of times. But here, to get to the first term, we have not added 4 at all. So we'll want to subtract 4 for A1. We're going to want to subtract 4 0 times. For A2, we should subtract it once. And for A3, we should subtract it twice. And so the number of times that you subtract 4 or add -4 is 1 less than the term number. And again, we can check this by looking at like A3. A3 is 7 minus 4 times 3 minus 1. The 3 minus 1 here obviously is 2, but that indicates that you should add the -2 twice in order to get to the -1 that is the third term. And so this is, again, 7 minus 4 times 2, which is then 7 minus 8, so -1. So this does work. Again, it's important to check that it works, but that's the rationale there. One more time, if we talk about this then as the fourth term and this is the fifth term, in order to go from A1 to A5, we should have subtracted 4 or added -4 4 times. So this n minus 1, where we get 5 minus 1 there, that's going to give us 4. That's going to tell us the number of times to do the subtraction, or the number of times that we should add -4. All right, and so an equals 7 minus 4 times n minus 1. That's an acceptable formula. This is for n greater than or equal to 1. We could put braces around it if we wanted to. We could distribute the 4 and simplify that more if we wanted to, but this would be another representation that would be okay. All right, if you have a second, you should pause the video and try this problem. So if I have, let's do 8, 15, 22, 29, and so on. So pause the video, see if you can come up with a formula for n starting at 0 and for n starting at 1. All right, so we should be getting an equals 8 plus 7n for n greater than or equal to 0, or an equals 8 plus 7 times n minus 1 for n greater than or equal to 1. Okay, so that's for arithmetic sequences. Again, arithmetic sequences are when you're adding the same thing every time or subtracting the same thing every time. Geometric sequences are another common example. And these end up being the most important in Calc 2 of the ones we're doing on this video. So let's look at an example of a geometric sequence. So let's say I have the sequence 2, 8, 32, 128, and so on. So to go from the first term to the second term, we multiply by 4, and then from 8 to 32 is times 4, and from 32 to 128 is times 4. So here we're multiplying by 4 every time. This is what is called a geometric sequence. So arithmetic is when you add the same thing. Geometric is when you multiply by the same thing. So we can approach this almost the same way. So if we call the 2 a sub 0, 8 is a1, 32 is a2, and 128 is a3, then to go from the 2, the a0 term, to the 8, the a1 term, you have multiplied by 4 once. To go from a0 to a2, you have multiplied by 4 twice. To go from a0 to a3, you have multiplied by 4 3 times. So to indicate that, we're going to start with the 2, and then we're going to multiply by 4 a certain number of times, and we're going to raise it to the n power, indicating that you should multiply by 4 that many times. So for instance, a sub 3 is 2 times 4 to the third, meaning you should start with the 2 and then multiply by 4 3 times, and then you can double check the computation, but you do get 128. A sub 2 is 2 times 4 to the second, which is obviously then 32. A sub 1 is 2 times 4 to the first. A sub 0 is 2 times 4 to the 0, meaning that you shouldn't multiply by 4 at all. And again, we remember that 4 to the 0 is 1, so we get 2 times 1, which is then 2. So this formula works for n greater than or equal to 0. You could use braces if we wanted to use those. We could write 2 times 4 to the n from n equals 0 to infinity. If we wanted to start at 1, so if we wanted to call this a1, a2, a3, a4, we can do that as well. But now for the first term, a1, you don't multiply at all. For the second term, you only multiply by once. For the third term, you multiply by 4 twice. So we're going to do 2 times 4 to the n minus 1. And this is for n greater than or equal to 1. Let's look at another example. So let's say I have 16, and then 8, and then 4, 2, 1, 1/2, 1/4, and so on. So here you're dividing by 2 each time or multiplying by 1/2. We're going to think of it as multiplying by 1/2. So I'm going to choose to start this with a0, a1, a2, a3, and so on. To go from 16 to the a1 term, you've multiplied by 1/2 once. To go to a2, you've multiplied by 1/2 twice. To go to a3, we've multiplied by 1/2 3 times. So it's 16 times 1/2 to the n, where the n exponent represents the number of times we should multiply by 1/2. So this is for n greater than or equal to 0. We can use braces, and we could modify this so that we start at 1 if we want to. When you have a minute, pause the video and let's try the next example. So see if you can come up with a formula for the sequence 81, negative 27, 9, negative 3, 1, negative 1/3, positive 1/9, and so on. So see if you can figure out the pattern there. It is geometric, but see if we can figure out why, and then pause it and come up with the video yourself, or come up with the formula yourself. Okay, so we should be getting 81 times negative 1/3 to the n for n greater than or equal to 0. Or if we start with n equals 1, we could do 81 times negative 1/3 to the n minus 1. Here you're multiplying by negative 1/3 every time. It's important that you can also write this algebraically as negative 1 to the n times 81 times 1/3 to the n, and you could do something similar on the one on the right. The algebra works out. Also, this negative 1 to the n makes it clear that this sequence is alternating, and so you'll see that a lot in examples that we do in the future. I want to look at a few more examples. So other types of sequences. This first one technically is geometric, but it's something that comes up quite a bit. So if we have the sequence 1, negative 1, 1, negative 1, 1, negative 1, it's clear what comes next. Obviously it's 1 and then negative 1 and 1, negative 1 forever. There's a couple ways to represent this. One way to do it is to do negative 1 to the n. And so this is where we would start with n greater than or equal to 0, because now if this is A0, this is A1, this is A2, and this is A3, -1 to the 0 is 1, -1 to the second is 1, -1 to the fourth is 1. So -1 to any even power is +1. And then all the odd powers, so -1 to the first is -1, -1 to the third is -1, -1 to the fifth is -1, and so on. And so this works for n greater than or equal to 0. If I wanted to relabel this where we start at a sub 1, we could fix that pretty easily. And so if we call this A1 and this A2 and this A3 and A4, we would say, okay, an equals -1. We could say n minus 1 here because now -1 to the 1 minus 1 is 0. -1 to the, -1 to the 1 minus 1 is -1 to the 0, which is 1. -1 to the 3 minus 1 is -1 squared, which is 1, and so on. If I put 2 in, -1 to the 2 minus 1 is -1 to the first, which is -1. -1 to the 4 minus 1 is -1 to the third, which is -1, and so on. So this would be for n greater than or equal to 1. We could also do an equals -1 to the n plus 1, because when we add 1 to whatever the number is, it changes the parity of the number, meaning it changes whether it's even or odd. -1 to any even power is +1, -1 to any odd power is -1. So this expression would work as well for n greater than or equal to 1. Something that's a little bit trickier is if we're alternating between two other numbers that aren't 1 and -1. So let's say I go between the numbers 8, 12, 8, 12, 8, and 12, and so on. And so there are several ways to go about trying to get a representation for the sequence. But one way to do it is to start with the 1, -1, 1, -1 thing. And since the smaller number is 8, we're going to make the -1s correspond to 8, and then +1s correspond to 12. So let's start with the sequence -1, 1, -1, 1, -1, 1. And we're going to try to make that into 8, 12, 8, 12. This sequence can be represented as an equals -1 to the n plus 1 for n greater than or equal to 0. And you can check that. If I plug in 0, I get -1. If I plug in 1, I get 1. If I plug in 2, I get -1, and so on. We want to turn this into 8, 12, 8, 12. So one way to do that is to look at the gap between -1 and 1. The gap between -1 and 1 is 2. The gap between 8 and 12 is 4. So we want to change the gap from 2 to 4. So in order to do that, we're going to double all of the numbers. So we're going to multiply by 2, because the gap here is 2 on the bottom sequence. The gap here is 4. So if I multiply by 2, then I get -2, 2, -2, 2, -2, 2, and so on. And now this isn't the sequence that we want, but it's spaced out by the same amount. So now to go to 8, 12, 8, 12, we can simply add whatever we need to get from -2 to 8 and from 2 to 12, and in both cases that's 10. So if I add 10 to everything, then I'm going to get the sequence that I want. So if I add 10 to this first value, -2, I get 8. If I add 10 here, I get 12. Add 10 here, I get 8. Add 10 here, I get 12, and so on. And again, you can verify the sequence works, but the expression on the right that I've circled does work for the sequence 8, 12, 8, 12. Okay, let's try one more like that. So if I have, say, 7, 10, we'll make 10 the first number, so let's make it 10, 7, 10, 7, 10, 7. So I want to start with 1, -1, where I keep the 1 corresponding to the higher number, -1 corresponding to the negative number, and get a representation for this. So this is an equals -1 to the n for n greater than or equal to 0. You could also make it an equals -1 to the n plus 1, or -1 to the n minus 1 for n greater than or equal to 1. But we're going to do it this way for now. The gap between 1 and -1 is 2. The gap between 10 and 7 is 3. So to go from 2 to 3, we're going to actually multiply by 3 halves. So if I multiply by 3 halves, I get -1 to the n times 3 over 2. Again, we're going to go ahead and say for n greater than or equal to 0. So then I get 3 halves, -3 halves, 3 halves, -3 halves, 3 halves, -3 halves, and so on. And that doesn't look like the sequence that we want, but the gap between 3 halves and -3 halves is 6 halves, which is 3, and that is actually what we want. So now to go from 3 halves to 10, we're going to add. If we think of 3 halves as 1.5, you can add 1/2 to get to 2, and you can add 8 to get to 10. So we're going to want to add 8.5, which is actually 17 halves. And so we're going to write it as an equals -1 to the n times 3 halves plus 17 halves for n greater than or equal to 0. If I add 17 halves to each of the expressions, or each of the fractions, 3 halves and -3 halves, we get what we want. So 3 halves plus 17 halves is 20 over 2, which is obviously 10. -3 halves plus 17 halves is 14 over 2, which is 7. And so this adding the 17.5 or 17 halves or 8.5 gets us the sequence that we want. Again, we can verify that this answer that I've boxed in is correct, but it does work. There are lots of other sequences we can try to get formulas for. They don't all follow this pattern, but this is some. The main ones that we'll see over and over again are arithmetic and geometric, and then we've looked at a couple others that happen to work. When you come up with other things, you sometimes have to be creative, but knowing arithmetic, geometric, and then how to use the alternating sequence 1 and -1 is helpful later. Okay, thanks for watching.